Yeah.
Okay. What's that?
Oh, really quick, I had a
I s-
question. I had a question about the first sprint synthesis.
yes.
One of the last question asks how much ethanol you would need to like melt a driveway full of water. What temperature is that ethanol at that we're melting the water with?
You are not melting the water. Stay tuned. Ask it later.
Oh, okay.
Oops. I accidentally assigned the person under you on the. Okay. I don't want to spend a lot of time belaboring the density issue because we did talk about it in the fall. But again, density is is really a measured property. It is not, in fact, a physical constant for a material. It is especially not a physical constant for a solution because it depends on a couple things, most notably temperature, but when it comes to solutions, also concentration. So if you need the density of a solution, for example, to convert the units of concentration, which we were doing on Friday, you really need the density of that solution of that specific concentration and also technically at that specific temperature. And so this is or isn't a problem, right? By which I mean you might know it, right? And so in this case, I had the density of that solution, right? If I don't know it, in a real world, I'm a chemist in the lab setting, I could always measure it, right? But that might be a lot of work, right? And I may not need to know it that accurately depending on what I'm doing. And so that's why I say this is sort of one of those areas that is more a life lesson than it is an actual chemical principle, right? Which is what to do when I need a piece of information that I don't specifically have. That's part of the reason I didn't give you a set of physical constants and delta H's and whatever for the homework, right? I mean, these days you can find anything you want with the internet, and we do, right? But finding that information is itself something of a life skill. And so the density issue, for something really well studied like salt and water, you can probably somewhere on the internet find the specific density at the specific temperature. For more exotic materials, that may not be quite so accurate, right? And so in that case, you have to decide fundamentally how well you need to know that number, right? And so in a totally made up example, right, if I have 2.5 molar sodium chloride, right, at 298 Kelvin, presumably, right, I need specifically the density of 2.5 molar sodium chloride, right? If I went to the internet, and again, totally fake example because I'm pretty sure I can find 2.5 molar on the internet, right? And I only find other concentrations, I am forced to decide what to do. There's really three options, right? There's two of them that really address specifically the solution issue. And so it really is a question of sig figs, right? If I want multiple sig figs, I really need the specific solution concentration density, right? If it's not 2.5 molar at the right temperature, I don't have a lot of sig figs, right? But if you look at the numbers there I do have, right, I've got 1 molar, 3 molar, and 5 molar. They are, quite frankly, all the same number to 2 sig figs. They are not the same number to 3 sig figs. And so it really becomes a question of whether I need 3 or 2 sig figs, right? If I need 4 or 5 sig figs, I'm really going to have to measure it, right? And so sometimes I assume, as much as you may hate that word and the process, I assume 3 molar is close enough, right? And I do that, quite frankly, because I am too lazy or too uninterested to try to get a more accurate number, but that is rooted in the fact that I don't need a more accurate number, right? It is really very much application specific. So if I can live with 2 sig figs, there's no reason not to make the assumption, right? Spending minutes or hours or days either searching the internet or trying to measure it myself to get sig figs I don't need is just a waste of resources, right? I can get approximately 3 sig figs if I do a linear interpolation, right? Again, we talked about this process in the fall, but essentially I assume there's a straight line dependence. This is, by the way, not 100% true for density. There is a concentration dependence, but it's not strictly linear, right? And, you know, as a more general tool, you can do linear interpolation. You can also do quadratic interpolation. You can do exponential interpolation. All you're really doing is assuming there's a functional form that your data should fit. Because what that essentially does is give me the data points in between my actual measured data. They're not 100% accurate unless, in fact, that is the correct functional form, but it does get me closer. And so if I fit the 3 points I have to a straight line, hey, look, now I've got a data point sort of for 2.5 molar, you know, and I sometimes refer to this as being 2.5 sig figs instead of 2, because again, I'm making an assumption about the functional form. All right. And even beyond that, if I really, really don't care about the sig figs, right, you'll notice all 3 of those are essentially 1 gram per milliliter to 1 sig fig. And of course, 1 gram per milliliter to 1 sig fig is the density of pure water, right? And so again, depending on the application, I sometimes feel free to just use a density of 1 gram per milliliter for a water solution, right? But I do it knowing that I really only have 1 sig fig left, right? If my concentration is really, really tiny, maybe I still have 2 sig figs, right? But it is a legitimate approximation method that really is essentially balancing the effort to get more sig figs against the value of having those sig figs. There are a lot of times, right, where I do need 4 or 5 sig figs, right? And that requires very careful work and possibly very careful measurement by me, right? There are other times where 1 or 2 sig figs is more than enough, in which case there is no point in spending man hours or resources trying to find a number I don't really need. Right. So sometimes I will assume a density of 1 gram per milliliter for a dilute solution where I don't need too many sig figs, right? Other times I will take the closest value I have. And sometimes, right, since a lot of our problems are somewhat synthetic in nature. Owl will give you exactly the density you need, right? Which may or may not be the real one, but at least it purports to be. Okay, and again, the whole reason I need to care about my solutions and the concentration is because when I have a solution and it's now a mixture, all the things we've been talking about in terms of the intermolecular forces are slightly different, because I've now created, by mixing a solute and a solvent, different intermolecular forces. And so in some cases, this creates a unpredictable change in property. All right. By which I mean, yes, you know, it is acetic acid and water, right? But it doesn't have the properties of acetic acid and it doesn't have the properties of water. And there's no easy way to decide what they are by mixing the two properties. There are other times, however, where the change in properties is predictable, right? And these colligative properties, that they're called, are kind of interesting and unusual and simple, in the sense that the change in property is strictly a function of the concentration. This is counterintuitive if you stop and think about it. It normally matters what the substance is, right? If you're making soup, you cannot substitute gasoline for chicken. I mean, you can, right? But they'll never let you cook again. All right. In the case of a colligative property, it would not matter. If you need a cup of chicken stock to make your soup, you could substitute, right, the equivalent amount of gasoline and you have exactly the same thing, right? In life, composition tends to matter. For the colligative properties, it really doesn't, because these properties are fundamentally statistical because of this whole concentration thing, right? We talked a little bit about, you know, mixing the solutions. I remind you of a couple things, one of which seems to confuse the issue a little bit on my my driveway problem, which, oddly enough, this week is a real problem. I think I have 2 inches of ice on my driveway. Right. If I have, and here's my static picture again, a solution, I have mixed in a certain number, right, of solute molecules into the water matrix, right? And this is what I mean about it being statistical, right? If I have a 2 molar solution, there's twice as many solutes as a 1 molar solution, right? If I have a 10 molar solution, there's 10 times as many solute molecules as a 1 molar solution, right? Now, right, we talked about the fact that, you know, there's 2 endothermic processes and 1 exothermic energy process involved. And we mentioned a little bit that the balance of those depends on what the relative magnitude of the energy is, but also the number of interactions. And so again, there's a statistical underpinning to this, right? In the sense that if I have twice as much solute, I expect twice as many solute-solute interactions and twice as many solute-solvent interactions, right? And the only thing that is really fundamentally different about those interactions is, since the molecules are different, right, I sometimes, not always, have the possibility of mixed interactions. And so in the case of something like heptane and pentane, 2 of my caterpillars, they're both nonpolar, neither one of them hydrogen bonds, right? They're van der Waal only, and so I now have still van der Waal only interactions, dispersion force interactions. You will note, though, from the drawing, there's a slight difference in the way the heptane and the pentane interact, because the pentane's shorter. If those were 2 heptanes, right, I have complete overlap of the heptane with another heptane. The pentane being shorter, gives me a slightly weaker interaction overall, but it's still strictly a dispersion force. If my mixed molecules are polar, or hydrogen bonding polar, or ionic, and my solvent is different, right? It's not polar, or it's not ionic, or it's not a dipole, right? You end up with these mixed forces. And so you might have a dipole-dipole interaction if you've got a polar solvent and a polar solute, right? You can have hydrogen bonding interactions. You can also have mixed interactions where the dipole, right, interacts with the hydrogen bond, right? So if you think of, if I put acetone, right, which has a dipole but doesn't hydrogen bond in water, right, I then have a mixed force, right? And so I don't know how many of these pictures we need to look at, right? I've mixed my solute in with the solvent. There is an energy change involved, but there's also a statistical disruption of the matrix. And that's where my colligative properties come into play, right? Of which there are 4 of them principally. 3 of them we'll talk about. I mean, the 4th one I'll sort of talk about, but I don't consider it that important because it's somewhat artificial. But the big ones, right, are the freezing point depression, the boiling point elevation, and frankly, vapor pressure reduction, which is really the reason the boiling point's elevated. All right. So, right, coming off our whole discussion of phase changes, right, if I have a solution, my phase change temperatures are all different, right? Water at 1 atmosphere pressure, right, boils at 200 or 373 and melts at 273. If it's salt water at the same pressure, it has a different melting point, a different boiling point. All right, and that's what the colligative properties are doing to my solutions. And it's relevant because, again, normally I have a solution, right? I mean, it's great if you want to freeze and thaw water all day, right? But if you're trying to do chemistry, there is usually reactants, in which case, you know, there's 2 or more reactants. Often in a solvent, there's, right, 3 species involved. And so I am not a pure substance that's freezing or melting or thawing or evaporating, okay? And so we'll talk about the first one just because it does lead us to the boiling point, right? Again, vapor pressure is that pressure of the vaporized solvent molecules above the surface of a liquid, right? And so if I happen to be a liquid molecule that has enough energy to escape, it does. This is actually a dynamic process, right? Where, you know, I evaporate, I bump into something that cools me down, I recondense, but while I'm doing that, something else, right, bumped into something, got enough energy and escaped, right? And that does require me to leave the liquid phase and enter the gas phase, right? If I were to have a solute present, right, I'm now a solution, right? I have essentially purely statistical blocking of the surface. Right? Some of my surface positions are now not occupied by the solvent, right? They're occupied by the solute. Right? That makes it harder for my liquid molecules to escape. There's essentially a ceiling above them that they bump into, right? And so having a solute present lowers the vapor pressure because it makes it harder to enter the vapor phase. And because it's really a statistical surface blocking phenomenon, right? The vapor pressure change due to being a solution tracks quite simply the concentration of the solute without really any concern for what that solute is. Now I know what you're thinking. What the hell happened to Kansas City? After that, you're thinking, but wait a minute. That just doesn't make sense. It has to matter. And you'd be both right and wrong. Because it both does and doesn't. Right? For the most part, right, there's very little concern for what the indication or what the specific solute is, right? But like anything else, if you take it to extremes, it begins to matter. If my solute is a small particle, it doesn't matter how many other different small particles I have, they're all small particles, right? If I replace that small particle with some giant molecule that blocks more of the surface, right, at some point my simple concentration dependence starts to care, right? One protein molecule will take up as much surface area as 200 or 300 small molecules, right? And so, you know, for extremely different solutes, right, it might matter, right? But in general, it does not matter. And so my vapor pressure ends up being strictly a function of the concentration of the solute. Right. And so, right, the functional dependence is fairly straightforward. It depends on a unit of concentration that we really don't use for, I think, anything else all year, except for this, which is the mole fraction of the solvent, right? Chi is a Greek letter, right? Mole fraction in general is moles of something over the total moles. Right. And so it's literally telling you what fraction of the particles are one of the components of my solution. Right. A lot of times when you're talking about a solution, right, it's the chi of the solute that people tend to talk about. In the case of vapor pressure, it's actually the mole fraction of the solvent that matters. And so, right, this subscript is just telling me it's solvent, so it's moles of solvent over the total moles of everything, which is the solvent and the solutes. Right, as you can tell from the functional form, mole fractions run from 0 to 1, right, because it is literally a fraction of the particles present. A mole fraction of 1 would be a pure substance. A mole fraction of 0 is kind of meaningless. It means you don't have any, in which case, why would you specify it? Right, I had coffee this morning. The mole fraction of gasoline was 0. Right, the mole fraction of blood was 0. I mean, you don't tend to specify what's not there, right? But technically, a mole fraction of 0 means you don't have any. A mole fraction of 1 means you're a pure substance, right? This P0, right, is the vapor pressure of the pure substance, right? And the P of the solvent in the solution is the vapor pressure of the solution. It says solvent in solution because my solutes are not volatile, right? And so I'm only talking about water in a water solution having a vapor pressure. If I have a saltwater solution, the salt has 0 vapor pressure. And so it's a fairly straightforward calculation if you want the vapor pressure, right, of something. So here's sucrose, a common table sugar, right? So I mix sucrose, C12H22O11, into water at good old 25 degrees C, right? And I want the vapor pressure of the water in that solution, right? And so, right, I have both a solute and a solvent. They are measured at this point in unfortunately different units, right? I have grams of sucrose, I have milliliters of water, right? If I'm talking about the vapor pressure of the solution, I technically need the mole fraction, which means I need the moles of water and I need the moles of sucrose. But that's okay, I know how to do both of those things, right? The grams of sucrose to moles is just the molar mass. We do that all the time. The water is what we were talking about Friday a little bit. I have milliliters. I can get to grams to get to moles, right? But volume to mass is density, and then mass to moles is molar mass, right? Those are our two favorite conversion factors for solutions, right? And then I also need the mole fraction of pure water, because again, my solution has its vapor pressure reduced based on the relative amount of solute and solvent, but it's reduced from the pure solvent, right? And so if I go to the internet or the textbook or phone a friend, right, the vapor pressure of water at 298 kelvins is 23.8 torr. Right. Since I already decided I needed both the density of water and the molar mass of water and sucrose, there's the molar masses of sucrose and water from the good old periodic table. Technically, if I wanted the max number of sig figs, I really want the density of water to 3 sig figs. It's pretty close to 1.00. To 3 sig figs at 298 Kelvin, it's 0.997, I believe. Right. And so if I convert the grams of sucrose to moles of sucrose, there's my friendly neighborhood molar mass. Right. And I convert the water to moles, right? I've got volume, the density again to 3 sig figs is 1.00 at that temperature. Right. Again, please note, right, that's not an exact conversion for grams to milliliters. That frequently gets overused as though it's some kind of physical constant of the universe. It is specifically the density of the liquid I have. All right. And so I have mostly water, which has to be the case, right? Because by definition, it's only a solvent if there's more of it, right? And so the mole fraction, again, I want the mole fraction of the solvent. So it's moles of water over total moles of everything, right? And so I had 16.65 moles of water over 16.65 moles of water plus the solute. If, by the way, there were 2 or 3 or 4 solutes, it would be the total moles of everything in the denominator. So, you know, if instead of just sugar water, this was my morning coffee, right? It would be sugar and lactose and caffeine and delicious flavor crystals. I don't know. All right. And so as you can see, the mole fraction is pretty close to 1. which you would expect since I'm talking about the solvent and there has to be mostly solvent. And so you just have a small decrease in the vapor pressure of the solution. All right. The vapor pressure of the water in the solution, right? Again, my sucrose is not volatile. It won't enter the vapor phase. The water will, but it's a little confusing the way it's written there because it says water in both cases, right? It's really this 0 that means pure, right? And so this is the water in the solution, right? And so that vapor pressure is 23.4 torr. What does that mean? It means the air is less damp, right? But more importantly, it also means the boiling point must have gone up, right? Because again, I only boil when my vapor pressure equals the atmospheric pressure, right? I'm now farther away from 1 atmosphere, 760 torr, right, for the vapor pressure. The vapor pressure went down. It's going to still increase with temperature as it always did for a pure substance. But if I'm going to boil, I have to get to 1 atmosphere, and I'm now officially farther away at 25 degrees than I used to be. Yes, no. Okay, so again, my vapor pressure depression, right, really ties directly to what's generally considered a different colligative property, but is really an extension of the vapor pressure, which is the boiling point issue. All right, and by a somewhat different mechanism, but similar, right, it also results in freezing point depression. And so I tend to talk of these two things as a unit because they functionally look a lot alike. Right. In the case of the boiling point, you know, if you buy my whole argument about the vapor pressure and the statistical blocking, right, it has to decrease the boiling point because the vapor pressure went down. There's a similar blocking mechanism that goes on with the freezing, which I'll show you a picture in a minute. And so they end up having the same functional form. Right. And I mentioned last week, this is the only place we see molality. Right. Turns out the change in the freezing point or boiling point is strictly a function of the molality. And that's what the M is for. It is technically usually written as a cursive M, which is hard to do. Right. But it's molality, which is moles of the solute over kilograms of the solvent. Right. This is a very simple expression. I often say it's, you know, everyone's favorite problem of the year because it's so simple. KB and KF are actually solvent properties, right? So you can look these up. Right, so what could be simpler? I have a number that equals a constant times a number, molality, right? So if I know the molality, which I have to for a solution, because it's meaningless to talk about salt water if I don't know how salty it is, right? So if I know the molality, I immediately know the boiling point and freezing point change, right? As long as I look up my KB and KF, right? Please note, right? I wrote it out here in terms of the difference in the temperatures, right? These are usually written just as the delta T, right? But please note, right? It's a delta T, it's not a T, right? It's the difference between the boiling point of the pure substance and the solution. It's not the boiling point itself on the left-hand side, right? Also, please note, this looks different on the internet and in OWL and most other sources because I insist on putting this negative sign here. In most places don't, right? And I do it because it's only logical, true, and right, right? Delta in all sciences represents change. And for sign convention reasons, it always is final state minus initial state, right? So a positive change means you went up from beginning to end, and a negative change means you went down for some bizarre reason that I don't know, right? They prefer, they being the Gen Chem gods, or at least the textbook authors, they hate the negative sign I put in there. And they would prefer to switch these two temperatures and make this positive. It is, of course, algebraically equivalent. They essentially move the negative sign to the left-hand side, right? But to my thinking, that's silly, because that makes the delta T of the freezing point the only time in any science where you have initial state minus final state instead of the other way around. And there's no reason not to put the negative sign on the other side. I don't know why. Historically, they hate it. But please note, right, that many, many sources will not put that negative sign there. Right. And the most important thing to note about that expression is the K is the solvent, right? Remember, it's a colligative property. It doesn't care what the solute is, right? And so it's the boiling point of the solvent because the solute doesn't matter. It's the K, B or the KF of the solvent because the solute doesn't matter, right? And so this is why you salt your driveway, right? Contrary to what many people have been thinking or saying. And it's frankly sort of common everyday parlance, right? And it looks like that's what's happening. You don't salt your driveway to melt the ice. You salt the driveway so the ice can't freeze in the first place. And you don't need to salt your driveway. You can throw anything you want in the driveway. You can throw sugar on the driveway. You will probably have ants in the spring because you'll have the sweetest driveway in town, right? But it doesn't really matter. You can, and I don't recommend this, you can throw gasoline on the driveway. Right? Then if you really want to melt it, you can just strike a match also, right? But in general, my goal in salting the driveway is not to melt anything. It's to make it so the water can't freeze in the first place. What I'm really trying to do is lower the freezing point to below whatever the atmospheric temperature is. This is why, for those of you who are from cold weather states, right, as you probably know, due to your thankful weathermen who are always warning you that life is about to end as you know it because, you know, weather Armageddon is coming, right? Salt stops working if it gets cold enough. right? And the reason is because you can't dump enough salt on the road or your driveway to get the concentration high enough to get the freezing point low enough, right? But for small temperatures below freezing, you can, and so you do, right? And so I threw sucrose in water before to change the vapor pressure. I can also throw sucrose in water to lower the freezing point, right? And again, the math here is simple, and there's only really two ways I can do it. I either have a target temperature I'm trying to get to, right? Or I have a solution already and I'm trying to figure out what the freezing point is. In this case, I'm trying to get to a freezing point of -3 degrees C. Why? I'm guessing it's -3 degrees C outside, right? If I want to sugar my driveway to lower the freezing point so my driveway is iceless, I need to get under whatever the atmospheric temperature is. And so algebraically, this is simple. I'm trying to get a 3-degree temperature change, so my delta T is, right, -3 degrees because it's going down. If I look up water, the KF of water is 1.86 degrees C per molal, right? Because it should end up being degrees C on both sides. So degrees C per molal times the molality gives me degrees C on the right. And if I do the math there, right, 3 divided by 1.86, I find out that a 1.61 molal solution will do that. Again, what I have fundamentally determined is really the concentration that matters, not the amount of sucrose. In this case, I'm going to use sucrose, but again, I could use anything, right? Because it doesn't care. It's a colligative property. 1.61 moles of anything per kilogram of water will lower the freezing point to -3 degrees C, right? So it doesn't matter if it's sugar or it's salt or, dare I say, hint, hint, wink, wink, ethanol. All right, if I'm trying to get to -3 degrees C, 1.61 molal will do it. In the case of it being sucrose in my 100 grams of water, right, I can then determine an exact amount, right? 100 grams is 0.1 kilograms times 1.61 moles per kilogram means that, again, I've now labeled it sucrose because I'm using sucrose, but 0.161 moles of anything will work. Since it's sucrose, all right, sucrose has a molar mass of 342 grams per mole, so hey, 55.1 grams of sucrose will work. Right. It's worth pointing out, if you stop and think about that number, that's why you don't sugar your driveway, right? That's 100 grams of water. I need 55 grams of sucrose, right? At that point, I'm approaching honey on my driveway, right? That's a lot of sucrose, right? My solution is now roughly 1/3 sugar and 2/3 water, right? This is not a dilute solution. Sucrose is simply too large a molecule to be effective unless I throw a whole lot of it, right? Which is one of two reasons I use, or I typically use salt, right? And so again, you can find tables of these things. The KBs and the KFs are material properties. They are virtually impossible to predict, at least in terms of magnitude. You'll notice they're all over the place, right? You'll see, in general, the more polar materials seem to have lower KBs and KFs, right? Benzene is nonpolar, carbon tetrachloride is nonpolar. Chloroform is very, very, very slightly polar, right? Whereas ethanol and water, of course, are both hydrogen bonding, so they're fairly polar. But, you know, as a general rule, you would never predict those numbers. I looked them up, right? And again, the change is relative to the normal boiling well, right, the normal boiling point, normal freezing point, as long as I'm at 1 atmosphere of pressure. Right, and of course you could do it the other way as well, which is if I have a solution of known concentration, right, I can determine its freezing point, right? In some sense, that's the more common way to do it, because again, we're trying to do chemistry here, not necessarily de-ice your driveway. And so typically I'm doing a reaction, that reaction has certain conditions, right? Concentrations of reactants in the water. And so inherently I've got a different freezing point and boiling point based on what I'm trying to do chemically. But you know, it's the same calculation in reverse. Again, it is algebraically the simplest calculation we do, since I'm always just sort of either multiplying two numbers or dividing two numbers. Right. In this case, because it's 1.7 molal, right, it's very close to the 1.6 from last time. So of course the answer ends up being close to 3.2. I stole this slide, so it doesn't even have my minus sign in it. Right, but you know, I can go one way or the other. Right. And boiling point works effectively the same way, only it's going the opposite direction. Right. The boiling point increases, the freezing point decreases. I think that gets you at least far enough to get that last synthesis problem done. So I apologize for skipping over some of those slides, but I really felt we needed to get here by the end of today. We'll talk about boiling point and osmotic pressure on Wednesday, and then on to kinetics, which is really one of the three largest topics for the entire semester. Questions or problems? Does that address the question we had at the very beginning? Right. But again, you're not trying to melt the ice on your driveway. You're just trying to keep the water from freezing. Okay, if you have questions or problems, I'm here. If not, happy Monday. Stay warm. It's one of those weeks.
Happy Monday. Thank you.
Thanks.
Thank you.
Thank you.